Yeah, now we can see perfectly.
Nice. Okay, so welcome, good morning, good afternoon, or good evening, wherever you are. So welcome everybody. So let me introduce myself. So I work as the Senior Director in a test and measurement company, where my work includes test equipment for semiconductors, aerospace, defense, transportation, and healthcare, and many other industries. While there are many differences among these industries, there are more similarities than you might expect, especially in the wireless area. At NI, our goal is to stay at the edge of new technology developments, to enable researchers and engineers to shape the future of technology. In many years, in the industry, time to market has always been a major concern for every project. So, however, there's no question that the pace of technical innovation is accelerating. And with the rate of engineering happening more quickly than ever, engineers are forced to accelerate every phase of the product development. We see this consistently in our industry, from the cost of being late to market to the race to be first. With an increasing need to be first, streamlining the engineering workflow has become more important than ever before. Inefficiencies in design and tests can have a significant impact on the release dates. Now let's talk about the wireless industry, especially about cell phones. Most of us probably have a 5G phone now. It takes about 8 to 10 years to create each new G, and people have been working on 6G actually for a while. As technology advances from 1G to 5G, things get more complex and perform better. So companies are dealing with more complicated designs as the market matures. This means they are shifting focus from growing revenue to actually making profits, which leads to less investment. So think about it. Soon, almost everyone who can afford a smartphone will have one. This surge in smartphones use brings new challenges. The amount of mobile traffic is expected to continue to grow almost 400% in the next 3 years. That means that we will see a lot of new bandwidth and not a lot of revenue growth. These two taken together, a flattened market combined with pressures to drive significant performance gains, are stressing many companies in the wireless space today, and this leads to many companies looking for ways to reduce their cost. Now, that being said, not all is grim in this space, and one of the biggest potential areas for growth is the area of non-traditional IoT. By this, I refer to the world of intelligent connected machines. So machines, drones, farming equipment, automobiles, robotics, acting in the world outside our homes that need to be connected to do their jobs. In a market that is searching for growth in new areas, while dealing with the challenges around the shift from a growth to a profitability mindset, it is a good time to pause, take a step back and rethink how we are all designing and testing the next generation of wireless technologies, especially with the advent of AI. As I mentioned before, devices are becoming more complex, and one of the biggest and most exciting ways these devices are increasing in complexity is the integration of embedded AI within their firmware and software in the future. The need to test AI to guarantee its function and trustworthiness is one of the biggest disruptions to happen to test in decades. While this is extremely exciting for the industry, it also makes testing these devices much more of a complicated task. The main challenge this poses for test is shifting from a classically designed or programmed system to one that is trained. Classically designed systems are predictable, which allows for a relatively simple stimulus response method for test. On the other hand, what happens when we integrate AI into, say, a braking system of a modern vehicle with several multi-megapixel cameras, radars, and LiDAR, and between a brake pedal? How do we define the set of input conditions that should result in the right amount of force at the brake pads? It's a much harder problem to solve, and the main issue becomes the unpredictability of the system. Now, I have teenagers, and I always say that teenage drivers are trained rather than programmed systems. As some of you may know, teenagers are unpredictable. Perhaps that's why their insurance rates are so high. So to cover the cost of this unpredictability. To put this in context, imagine every single car being driven by a teenager. How unpredictable of a world would that be? So I'm German, and the thought is much scarier if you think about the Autobahn not having a speed limit, 200 kilometers per hour. How terrifying would that be? In the same way, it is true for these AI embedded cars. On one hand, we can't afford to achieve 100% test coverage when the set of possible conditions is infinite. On the other hand, what is considered a pass versus a fail is much harder to define. If the AI powering the perception engine in your vehicle misrecognizes a fire engine as a school bus, but the vehicle still comes to a safe, complete stop when it is supposed to, is that a pass or is it a fail? And if it is a fail, what new training data would you need to add to your training set to fix the misdiagnosis, but not break anything else? So these are the types of difficult challenges we are faced with when embedding AI into our next generation wireless networks. It is a new era for us wireless engineers, but perhaps there are some things we can learn from other industries like automotive that have been working on this problem for a decade. Now, before we continue to dive deeper into AI ML, let's switch back to cellular, specifically 5G Advanced and 6G. As we discussed earlier, the challenges in the wireless space have both business and technology components. How do we serve the evolving needs of our existing customers as efficiently as possible while searching for new applications of wireless technologies? Embedded AI might just be the key. As wireless spectrum is one of the most valuable finite resources we have, it should come as no surprise that optimizing the spectrum we have and expanding into new frequency bands in a cost-efficient manner are two hot topics. AI is especially good at finding and recognizing patterns. It is also uniquely good at the optimization of nonlinear, hard-to-model problems. And many, if not most, of the new technologies being discussed in 3GPP, for example, fall into one of these two buckets. The cognitive radio capabilities that will likely be needed in spectrum sharing in the FR3 bands, as an example. Also, the imaging-like sensing capabilities needed to implement the integration of communications and sensing, and the beam steering, beam forming functions in advanced MIMO. AI technology offers potential in areas like spectrum efficiency, user experience, and resource optimization to achieve our top technical and profitability goals. Yet, given the complexities of designing and testing AI solutions, overuse can also be counterproductive. So optimize for classical designs when feasible, and reserving AI for challenges where fixed implementations fall short and cannot be implemented accordingly. With rising device complexity, trained AI implementations will prove more efficient for an expanding range of problems. With this in mind, there can be both compelling business and technical reasons to use embedded AI where appropriate for optimizing system profitability and performance. At this point, embedding AI into wireless devices becomes a question of when and not if. And the new question arises, how do you embed and test trustworthy AI? At the core, we need three things to effectively design and test trustworthy AI in our future wireless systems. First, you need a sufficient quality and quantity of training and validation data. Second, you need some reasonable complete method of testing your AI implementation. As we discussed earlier, the traditional stimulus response models for testing simply don't work for these devices. So how do you solve for this? And third, leveraging AI to test AI will be instrumental. Simple enough, right? Now let's start with the data. As I mentioned, the most important thing you need is the sufficient quality and quantity of training and validation data. Without a rich data set that covers all the primary anticipated uses of the AI, you cannot develop and test a trustworthy system. This data can come from a variety of synthetic and real-world sources. As it will be likely a data set of significant scope and size, that data set will also need to be curated, managed, labeled, processed to be ready for building and testing an AI implementation. This is a space that NI has played in for some time. Through record and playback hardware and software, we can provide a platform that can collect the data from the virtual and real world. But from there, the question becomes, how is that data stored so it can be broadly consumed? Under an NSF grant, NI has been collaborating with a leader and pioneer in the field, Northeastern University, on a project called the RF Data Factory to create new tools that can automatically capture data in a standard format. So we released the RF Data Recording API as open source code that all researchers can access free of charge in GitHub. The Data Recording API requires a single text-based configuration file to configure complex scenarios with multiple RF transmitters and RF receivers over a large range of parameters. The code runs on the NI AIML research hardware and software platform, the NI software-defined radios USRPs, and enables researchers to capture real-world data. The recorded IQ samples are saved in so-called signal metadata format, in short, SIGMF format. A second. It provides comprehensive scenario descriptions by means of the JSON-based SIGMF metadata files, which are human readable and easy to parse. This will simplify the management of dataset libraries and the adoption by the research community. So once you solve for data, you need some reasonable complete method of testing your AI implementation. As we discussed earlier, the traditional stimulus response models for testing simply don't work for these devices. So how do you solve for this? I propose we take a look at an industry that has adopted scenario-based testing for a few years, automotive. Using the automotive space as a starting point, we can create and manage a set of scenarios, system-level test cases that provide insight into how an AI/ML-based implementation will perform under real-world conditions. Given the number of scenarios possible, you will want to do as much testing as you can in the virtual world using software or model-in-the-loop methods. So this chart represents the entire development cycle of a vehicle, from its concept development and design to its production. The colored arrows represent the overall test approaches along a typical design lifecycle. Now, moving from left to right, engineers in this space gradually move from testing the isolated machine learning model to testing a deployed version of the entire system in the real world. As an engineer, staying at the model level allows you to iterate quickly, trying and testing new designs quickly, and with fewer resource dependencies. As you move to the right, you increasingly implement more of the system around the AI-based model at the pure software level, followed by building the actual deployed hardware module, but connected to emulated versions of the sensors and actuators in the system. Lastly, you test the final modules in a complete vehicle. At each stage, you get increasingly complete information on the ultimate performance of your implementation, but at a slower, costly rate. A similar design and test flow could also make sense for wireless AI-based implementations, starting in purely software-based test setups and progressing towards field trials and deployments. Now, we just saw a progression of how to move from AI-based models to practical implementations. The next question to answer is what to test. Also borrowing concepts from the automotive space, here's a view into how to scope the potentially infinite number of scenarios needed to fully validate an ML-based design. The process starts with defining a finite number of functional scenarios that are meant to demonstrate and measure how the AI behaves in achieving specific measurable performance metrics or outcomes. For example, imagine we need a car to be able to safely merge into a traffic in downtown Manhattan during a blizzard. The first step is to break down each functional scenario into a larger set of logical scenarios. Here we begin to introduce each of the configurable parameters of the system and the ranges of those values that match the functional scenario from which the logical scenario can be derived. And finally, each of the logical scenarios is broken down into a concrete scenario which contains a very specific set of parameters. As a very long list of discrete parameters, a concrete scenario is easy for a computer to apply to the virtual or physical system. But at this point, it is difficult for a human to understand the behavior of the configured end system. In the same way, the vehicle is attributed a set of parameters. Our current hypothesis is that you can break down the wireless parameters into 4 fundamental categories. Parameters needed at an application level, information about the wireless environment or channel, the configuration of terminals that are communicating wirelessly, UE in the base station, for example, and information about competing traffic. Combining these two views of the workflow and the scenarios, we've built a system that takes the concrete scenarios application, environment, terminal, and traffic parameter spaces and applies them through a test execution engine to a full emulation of a real-world implementation. In the picture at the bottom of this slide, imagine we are trying to test an AI-based implementation of a base station receiver, optimizing and tuning its performance. We can execute the system in the yellow dashed line virtually, using model-in-the-loop and system-in-the-loop methods in the early stages of the design. As we get close to field trials, we can replace the base station or UE emulators with real devices. We can replace the mathematical channel emulator with a physical channel emulator, and so on. As testing advances, we move from testing the system from a completely virtual model to the real-world model, to a world where we test the algorithm with real-world but emulated channels, traffic, and applications, and finally to field trials. Okay. In recent conversations with one of the telecom operators in Europe, they expressed a strong desire for testing methods that can definitely show 2 things. One, the performance or business gains of an AI-based implementation compared to their existing classical implementation. And secondly, some estimate of the risk of deploying that AI-based implementation. These systems must perform. So it makes sense that they want to be pragmatic about the trade-offs, as they only want to deploy and implementations where the gains outweigh inherent risks of an AI-based solution. And there are no specific tools today that can provide that insight. Using the two perspectives described in the last couple of slides, we've begun to prototype these functions as a way to efficiently develop and test these new implementations in a way that our operator customer would find compelling enough to make a business decision. In our early prototypes, the AI model we've chose to use for this testing is an implementation of an AI-trained receiver based on the DeepRX implementation described in the literature. We've trained this model with both synthetic data as well as real-world data, which we've captured and managed using the RF Data Factory open source tools I mentioned earlier. And to make the system both affordable and accessible, we are using open source implementations of the base station and UE IP as containers into which a researcher can add their IP under test. Here are some early results where we are comparing the performance of bit error rate versus the signal to noise ratio per bit of the system for a set of traditional and AI-based implementations. The last thing I'd like to touch on is the increasing reliance we'll have on AI to test AI. AI has the potential to help hyper-automate the exploration and validation of the limits of an AI-based implementation through auto scenario generation and through techniques designed to find the areas where the AI's output is most sensitive to small changes to its input. The question becomes, of the infinite number of scenarios I could test, which are the most important and which can I eliminate? Here we are researching a method starting from a set of seed scenarios that can make use of the gradient function of the inherent neural net implementation to create sets of derivative concrete scenarios that maximize the test coverage of each neuron within the neural net and attempting to find areas of the model that have inconsistent outputs with small changes in inputs. Optimizing neuron coverage makes some intuitive sense. If in our attempt to reduce testing burden, we leave a portion of the implementation completely untested, that represents a coverage gap. In investigating derivatives where the model is most sensitive allows us to find areas of potential instability. Referring back to our automotive example, perhaps our perception is most sensitive to white cars at an intersection in a blizzard. This example is unintuitive, but our experience with these implementation is that there are always sensitivities in trained models that are less intuitive, and our hypothesis is that using the mathematical gradient function of the deep neural net can help us to find these efficiently. While these three pillars seem conceptually simple, there's a significant amount of work that goes into making them a reality. So at NI, we invent instrumentation, hardware and software that enables scientists, engineers and enterprises to make measurements on the performance of the technology they are inventing, which in turn also gives them business insight into the effectiveness of their engineering and manufacturing process. Across the globe, engineers are working on solutions to some of the society's greatest challenges, from finding new sources of renewable energy to providing entertainment and productivity solutions to consumers. We believe in the creativity and ingenuity of engineers to create solutions to these grand challenges. And if we can accelerate the productivity and discovery of those engineers, we can make a huge impact on the world. We also believe that measurement of the performance of the products a company invests are huge key in helping those companies unlock greater product and the business performance. Some people view test both in terms of cost and time as a necessary evil, but I don't see it that way. When done strategically and in a well-integrated way, measurements and the insight they unlock can speed time to market, improve customer satisfaction, and reduce operating costs and position companies as market leaders. Thank you so much for having me here today.
Thank you very much for this very interesting talk. So we are running out of time, but I think that we have time for one question that I will read from the chat that says that, can we use neural networks to do the digital predistortion of the transmitter nonlinearity when the signal bandwidth gets higher and higher?
I'm just referring to what's actually happening right now and what we are facing today right now. We are seeing that there are some ML DPD implementations already being done by leading chipset manufacturers. And we, from a test and measurement company, are actually faced with those machine learned implementations, because after the DPD, some PA type testing needs to be done. So that has an impact on how you test the PA along the signal chain. And so I think, yes, MLDPT is a topic. With respect to higher bandwidth going forward, I would say that is certainly something we can expect.
Okay, so thank you very much again for joining this seminar and for this very nice, interesting talk. I think that we all have enjoyed this presentation. So then, without further delay, I will pass to the next couple of speakers.